Hi, I'm Daniel Chan from UNSW Sydney. Welcome to another adventure in pure mathematics. Platonic solids are beautifully symmetric objects, and in this video I want to talk about the rotational symmetry groups of these Platonic solids and analyze them using the theory of group actions that we've set up in this playlist. The other thing that I want to do is that I want to show you how, starting from the rotational symmetry groups, you can actually, in some sense, almost recover the original Platonic solids. So the study of these two things are actually intimately linked. Okay, so let's start with trying to say something about what is a Platonic solid. So hopefully you know what they are. There are 5 of them. There's the tetrahedron, cube, octahedron, dodecahedron, and icosahedron. And the way I want to describe them, rather than giving a formal description, is to say they're three-dimensional polyhedra which are maximally symmetric. Okay, so this is some sort of a generalization of how you might want to think about a regular n-gon. Okay, so a regular n-gon, that's a very symmetric-looking object. Okay, and how is it symmetric? Okay, so it's symmetric in the sense that all the sides of a regular n-gon are the same, and all the vertices, they look the same. Okay, so that's in what sense I want to talk about a Platonic solid, and that's how I want to think about it in this video. Okay, so it's a polyhedron which is maximally symmetric in the sense that up to rotational symmetry, all the faces look the same, and similarly for the edges and the vertices, all the edges will look the same and all the vertices will look the same. Okay, so what do I mean by that? So here's a typical Platonic solid. Here's the cube. Okay, and I've got some different colors on the sides, but if they were all the same color, it would be perfectly symmetric, just like the cube has maximal symmetry. Okay, so let's just see what I mean by all the faces look the same. Well, this top face is just like this face on the side here, and they play a similar role. Okay, so in other words, there should be some rotational symmetry of this cube which sent this side face to the top, and certainly there is. Okay, similarly, all the vertices look the same. So for example, this one and this one here, they look the same. So there should be some rotational symmetry which sends this vertex to this one. So we can sort of just rotate like that, okay, 180 degrees around the vertical axis. Okay, so that's in what sense I mean by maximally symmetric. Okay, so let's go through these 5 Platonic solids, and let's just look at some of the features that they have. Okay, so I've listed in this table the number of faces they have, the numbers of edges per face, the number of vertices, and the number of edges per vertex. I haven't listed out separately the number of edges, but you can work it out from these pieces of information, either this column or this column here. Okay, so maybe I'll just do the cube so you know what this table encodes. Okay, so cube is easy enough. Okay, so firstly the number of faces it has, top, bottom, 2 sides, and front and back. So there's 6 there. Okay, so it has 6 faces. So that's the first thing that we have here. 6 faces. And then, of course, what shape are the faces? Okay, they're squares. So the number of edges on each of the faces is 4. So there's a 4 here. So 4 edges per face. So 6, 4 means there's 6 square faces. What about the number of vertices? Okay, there's on the top 1, 2, 3, 4, and similarly on the bottom 1, 2, 3, 4, another 4. 4 plus 4 is 8 vertices. 8 vertices like that. And the number of edges per vertex, so what does that mean? So let's take a vertex like this one here and look at the edges that come out. Okay, there's 1, 2, and 3. So the number of edges per vertex is 3. Okay, so let's go through this list of Platonic solids to see what they look like. So the first one here is a tetrahedron. It has 4 triangular faces and 4 vertices. The octahedron, that's this one here. Okay, it has triangular faces, 1, 2, 3, 4 on the top, and another 4 on the bottom, so 8 triangular faces. And the number of vertices, 1 at the top, 1 on the bottom, 2 plus a 1, 2, 3, 4. It's like a square in the middle. So that 2 plus 4 is 6. And at each vertex, you can see there are 1, 2, 3, 4 edges coming out. So there's a 6 and a 4 here. And just to run through briefly, the dodecahedron has 12 pentagonal sides. The number of vertices is 20. And at each vertex, there are 3 edges coming out. And the icosahedron has 20 triangular faces. So 20 triangular faces, and there are 12 vertices, and at each vertex there are 5 edges coming out. Okay, so that gives you a description of these 5 Platonic solids. And if you look at this little table, you might notice something rather interesting. Okay, so here look at the cube here and the octahedron. Okay, so firstly, these numbers 6 and 4 occur over here, 6 and 4. The numbers here corresponding to the vertices 8 and 3 recur over here, 8 and 3. In the case of the tetrahedron, the numbers here 4 and 3 get repeated over here, 4 and 3. Let's have a look at the bottom 2 rows and notice what happens. Okay, so here you have 12 pentagonal faces, 12 and 5, and for the icosahedron, the 12 goes with the number of vertices and the 5 goes with the number of edges per vertex as opposed to edges per face. So these numbers swap over here, and similarly these numbers here swap over here. Okay, and actually you may wonder, well, what's happening? Okay, is there a deeper explanation for that fact? And there is indeed, and that's something called duality. Okay, so that's something that I want to explain next. So duality is something which swaps the roles of the faces and the vertices. And what it will do is it will swap the roles of the cube and the octahedron and the dodecahedron and the icosahedron. So they're quite related to each other. Okay, so let me show you how this process works on a little example. So here's our cube. And what I want to do is, given some sort of Platonic solid, I want to construct a new Platonic solid where the roles of the faces and the vertices get swapped around. Okay, so how do I do that? Okay, so here's our cube. And what I'm going to do is, for each face, I want to replace it with a vertex. So I might as well just pick the midpoint of each face. Okay, so I've got to replace it with the midpoint of each one. Okay, so now I want to join up these vertices so that you get edges, and then those edges you'll fill in to get faces. Okay, so let's see how we do that. Okay, so we've got all the 6 faces are now 6 vertices. So you might see, by the way, that that's the same as the number of vertices of the octahedron, and that's what you have. Okay, so if you just have the midpoints of those faces, you'll get precisely the vertices of some octahedron. Okay, so how do you actually get the rest of the octahedron, not just the vertices? Okay, so let me show you how. That's quite easy too. Okay, so let's have a look at one of these vertices. Okay, we're going to look at this vertex, say here. Okay, and let's move away a little bit from the vertex and just go around it in the neighborhood. Okay, so you might start with one of the faces, and then you cross an edge to another face, a second face, then you cross another edge to go to a third face, and then you cross the last edge to go back to the original, this back face here. Okay, so that's what happens. Okay, so as you go around this vertex, okay, in a neighborhood of this vertex here. Okay, so what we're going to do is, we've got the vertices, okay, they're the midpoint of all these faces. And what we're going to do is we're going to traverse around the same way. Okay, so what do we do? So we went from a face across an edge to a face. So this edge now will become an edge in the transverse direction. So you join up these 2 midpoints. That's an edge corresponding to this edge of the cube here. Okay, now here's another edge that you cross from this face to this face. So now you have in the dual polyhedron an edge from this face, the midpoint of this face, that vertex, to this vertex here. And finally, when you go from this face to this face across this edge, you replace that with an edge in the transverse direction. So you go from the midpoint here to the midpoint on the back here. Okay, midpoint on the back, and that gives you a new edge. So you'll get a triangle here. Okay, and this vertex will be the face which contains those that triangle. Okay, as a boundary. Okay, so that gives you a triangular face. It's essentially by cutting that off. Okay, so you do that with each of these vertices, and what you'll find is that each of these vertices will become some triangular face. Okay, and I hope you can see what happens is, in fact, you get precisely this octahedron. Okay, when you do that. Okay, so for example, here you have a vertex in the corner here, and that corresponds to, well, now you've chopped off that thing, right, that vertex, and it becomes this triangular face here. Okay, so this was the top face. Before you had a top face, a front face, and a side face. They get replaced by the midpoints. Okay, and then as you go around the various edges, you replace them with edges, and that vertex becomes a face instead. And if you do that with all the vertices, what you'll get is this octahedron. Okay, that's great, isn't it? Okay, so this is a way that you can actually swap the roles of the faces and the vertices. But of course, in the process, you'll change from one Platonic solid to another one, at least most of the time. Okay, so what we find here is this notion of duality. And duality means that when you do it twice, you should go back to itself. Okay, so you can ask, what happens when you try to do this process to this octahedron? Okay, so now what you might want to do is you take the midpoints of all these faces, and they're now vertices. Okay, so you can see in the top there, you've got 4 triangular faces, so their midpoints now give you 4 vertices. And of course, if you join them up, as you would joining them transverse to all these edges, you'll get a square. And that becomes the top face of this cube. And if you repeat this procedure, what you'll get is that using this duality, when you do this procedure, you'll get back the cube. So there'll be a cube inside that, so to speak, which is a dual cube. Okay, that's great. So this gives you an explanation for the numerics that we see here, the numerology that you see here. So it turns out this cube and the octahedron, they're dual to each other. Cube and the octahedron are dual. And the dodecahedron, when you apply this duality to it, you swap the roles of vertices and faces, you'll get the icosahedron. And of course, when you apply it to the icosahedron, you'll get back to the dodecahedron. And finally, there's only one left, the tetrahedron. What happens when you apply it to the tetrahedron? It turns out if you try to do this procedure, you'll just get back another tetrahedron. And that's why the numbers here get repeated over here. Okay, so the interest for us is we're interested in studying the rotational symmetry group. And it has a very, very interesting corollary. Okay, so let's suppose that the rotational symmetry groups, I've denoted them with GT for the tetrahedron, GC for the cube, GO for octahedron, GD for dodecahedron, and GI for the icosahedron. It turns out then that the rotational symmetry group of the cube equals the rotational symmetry group of the dual polyhedron, or Platonic solid, the octahedron. And similarly, the rotational symmetry group of the dodecahedron actually equals the rotational symmetry group of the icosahedron. And it's in fact very, very easy to see why. Okay, so you're saying that basically they have the same rotational symmetry group. Okay, so remember, how do I get the octahedron from the cube, for example? Okay, so all I did was I just replaced all the faces with the midpoints, and then I replaced the vertices with the faces in a slightly more complicated procedure. Okay, so now let's take any rotational symmetry of this cube. So for example, I rotate it about a vertical axis. Okay, so you should think of this octahedron as being inside this because the vertices are the midpoints of the faces. So as you rotate it like this, you will also rotate this the midpoints of the faces, and hence the whole octahedron in the same way. And of course, what you'll get back when you've rotated is the same thing. So when you construct this dual object, you get back this octahedron too. So in the process, you've actually rotated the octahedron back to itself. So every rotational symmetry of the cube induces a rotational symmetry of the octahedron. Okay? But what about conversely? Are there some extra rotational symmetries of the octahedron which you don't find in the cube? Well, the thing is that, well, there's a little cube that you can stick inside here who has vertices, the midpoints of all these faces. So each time you make a rotation of this octahedron, it will also rotate the cube inside. Okay, so that gives you a one-to-one correspondence between the rotations, which are symmetries of the cube, and the rotations which are symmetries of the octahedron. Okay. So when you pass to the rotational symmetry groups, unfortunately, these 5 objects get reduced to 3 rotational symmetry groups. Okay, so there's this one here, and the rotational symmetry group of the tetrahedron. Okay, so let's now try to apply some theory of group actions to study these groups. Okay, so firstly, what I want to do is I want to fix one of these Platonic solids, and I'll call it P. G is going to be the rotational symmetry group. And F is just going to be the set of faces. Okay. We'll let little f be a particular face. And remember, the group G acts not just on the Platonic solid. Since it acts on the Platonic solid, it also acts on the set of faces. So G acts on this finite set of faces F as well. So since this acts on this face and you have an element inside this G set F, you can talk about stabilizers of elements inside here. So what's the stabilizer in G of F? Well, I claim that it's quite easy to say what it is. It's the rotational symmetry group of a face. Okay, so for example, here's a cube. Okay, and suppose you pick this top face here. Okay, and then I claim that the stabilizer in G of F is just the rotational symmetry group of this square. Okay, so you can rotate it in 0 degrees, 90 degrees, 180 degrees, or 270 degrees. Okay, it can be those four things. So in particular, since the rotational symmetry group of a face, how many elements are in there? What's its order? This order is n is just the number of edges per face. Okay, the number of edges per face. So that's just the number in this second column here. Okay, the number of edges per face, and that gives you the stabilizer. And it's very easy actually to see why this is true. Okay, and it uses the maximal symmetry. Okay, so the key point is the following. Okay, the Platonic solid is a maximally symmetric object. Okay, so you can look at the top faces, all the faces are the same, but also you can look at the face this way and it looks the same as if you look at it this way. Okay, over this way. And that corresponds to the fact that you can rotate that top face like this and it looks just the same. And part of maximally symmetric means that, well, that means that actually you can rotate the whole of the, this Platonic solid, and it will stick to that rotation of the top face. Okay? So what you find is that certainly all the rotational symmetries of a face of a Platonic solid give you elements in the stabilizer. And what other elements of the stabilizer do you have? Well, remember, what are the rotational symmetries of a Platonic solid? Well, the axis has to go through either a vertex, okay, or the middle of an edge, or middle of a face. And of course, if you want to stabilize this face, the only way you can do it is if you have a vertex which goes through the middle of that face. Okay, and then all you can do is just spin it round. That's the only way you can stabilize that face, keep the face rather than rotating it elsewhere. Okay, you have to have some axis of rotation which goes through the middle of that face, and that guarantees that you've got a rotation which stabilizes that. Okay. And then you just have to look at, well, how many ways can you rotate it? Okay, and it's the same as the number of ways you can rotate that face. Okay, each of them induces an actual rotation of the whole Platonic solid. Okay, so that gives you this result here. The stabilizer is precisely those symmetries where you have some axis which goes through the middle of the face, and then you just look at all the rotational symmetries about that axis of that face. Okay, so they number the number of edges of that face. Okay. So now we can state some nice theorem which gives you an easy way to calculate the order of this rotational symmetry group, okay, and also tells you some interesting facts about it. Okay, so the order of this G is just equal to the number of faces times the number of edges per face, and that's also equal to, as you can guess, well, why do we pick faces as opposed to vertices? They have fairly dual roles anyway. Okay, so there's some sort of strange symmetry between them. And the thing is that there's nothing, so it's also equal to the number of vertices times the number of edges per vertex. Okay, so let's go through the orders of all these three rotational symmetry groups. So for the tetrahedron, okay, you can do number of faces times the number of edges per face. That's 4 times 3. So that's 12. And the other product is in these two columns, 4 times 3, so that's the same. So for the cube and the octahedron, you can do 6 times 4. Or you can do the number of vertices times the number of edges per vertex, 8 times 3. And so what does that equal? 24. It doesn't matter how you calculate it. Okay? So when you do the octahedron, of course, you get the same numbers, except for these have swapped around. Okay, so the same products appear. And finally, the products that appear for the dodecahedron and icosahedron. You have 12 pentagonal faces, so you have 12 times 5. That's one possibility, and the other one is 20 times 3, or 20 times 3 here. So in both cases we get 60. So the order of this rotational symmetry group here is 60. Okay, now let's go ahead and prove this beautiful theorem. Okay, so what we'll do is we'll have a look at this G set F, and we're going to use maximal symmetry. So remember, maximal symmetry means that all the faces, in particular, of a Platonic solid, they look the same, right? So what does that mean? So given any face, you can rotate it to any other face, okay, because all the faces look the same, okay? So given any face, you can rotate it to any other face. So in other words, in terms of the theory of group actions and the language set up there, that means that this F has a single orbit, okay? And that orbit you can take to be G dot F, written like that. And remember, one of the things that we have is a complete structure theorem for G orbits, okay? So any G orbit, we can say what it looks like, okay? It has to have the form G mod some subgroup, and that subgroup is given by the stabilizer of some element inside that G set. So it's a stabilizer of that F, okay? So remember, this is the set of all cosets, and that has a natural G set structure, okay? So these are isomorphic as G sets, and in particular, the only thing we really need to know is that they're in bijection with each other, so they have the same number of elements, okay? So the number of elements here, that's the set of faces, that's just the number of faces that we have, okay? So that cardinality has to equal the cardinality of this. And the point is that we can also write out the cardinality of this in terms of the cardinality of G, the order of the group, and also the order of this subgroup, the stabilizer. In fact, it's just the quotient, okay? So it's the order of G divided by the order of the stabilizer of F. And the thing is that in this lemma, we saw precisely what this is, okay? This is just a rotational symmetry group of a face, okay? Where you rotate using an axis through the middle of that face, okay? So how big was this? This was just the number of sides of that face, or number of edges per face, okay? So now we have an equation here. Number of faces equals the order of G divided by the number of edges per face. So to get the theorem, you just have to put the denominator to the other side to rewrite the order of the group as a number of edges per face times the number of faces. Okay, so that gives you one version of the theorem, one half of the theorem. The other half involves vertices and the number of vertices and the number of edges per vertex, and you can prove this in the same way. Okay, and this is a complete proof of this rather nice theorem. Okay, so the next question that I want to have a look at, which is really interesting, is the following one. Suppose you just have the rotational symmetry group G. It's just some finite subgroup of SO3. Okay? Can you recover the Platonic solid P from it? Well, of course, the answer as it stands is no, because there are pairs of Platonic solids with the same rotational symmetry group. Okay? So the cube and the octahedron, they're dual, and the dodecahedron and icosahedron, they're dual. So we can at best only recover up to duality. And the question is, can we do that? And the point is, if we can, then there's a very, very strong relationship between these two objects, and suggests that they're very, very important mathematical objects, and we'll see, in fact, that it's related to lots and lots of different things. Okay, so we'll find out that essentially we can do this, and the answer uses some more interesting notions in the theory of group actions, and that's the notion of a fixed point set. Okay, so this is fairly general, so we'll start with the general setup here. Okay, X is going to equal some G set, and we just have some subgroup H of that G set. Okay, so what we can do is we can talk about the fixed point set of H in this X. Okay, so that's some subset of this X. Okay, there's some of the elements in there, and which ones are those? They're the ones which are fixed by every element of this subset H. So all the little x such that H dot X is equal to X for all little h inside here. Okay, so it's just some subset of X, and the definition should be fairly clear from the terminology. They're precisely the elements which are fixed by all of the elements inside here, like that. So let's look at a simple example, and one that's going to be very relevant when we try to study Platonic solids. Okay, so here we're looking at rotations. And let's look at the full group of rotations, G equals SO3, and we'll let it act. Well, of course, it acts on all of R3, and in particular on the unit sphere inside there. Okay, so we'll act on the unit sphere. And let's just pick one rotation, okay, like this. So I guess we can move the sphere around so that it rotates about an axis like this. And let's suppose it's not the identity rotation, so it actually rotates. Then the point is, what is the fixed point set? Okay, can you describe SG? So what gets fixed by this rotation? Okay, so it doesn't move when you apply that rotation. When you rotate, that point is the same as the original one. And of course, it's just where this sphere intersects the axis of rotation. Only on the axis of rotation do things not move. And so, of course, they're the two poles. Okay, the pole here and the pole here. Okay, so just the two poles of this axis rotation on that unit sphere. Okay, so that's a way from going from a rotation to points on the unit sphere. Okay, so that's what happens here. Okay, so we're going to generalize what's going on here. Okay, so remember in this question we're starting with a group of rotations, and we want to recover some Platonic solids, some points at least. Okay, some set of points. Okay, so this is a way to do that. Okay, so here's our proposition definition. Okay, we're going to look on the unit sphere. Okay, so I guess each of these Platonic solids, you can find a circumscribed sphere for them. Okay, and we're going to say an element of that unit sphere is a pole of this group G if either of the following equivalent conditions hold. So here are two conditions, A and B, and this is condition S. So the first one is that this S lies in some fixed point set, SG, where G is some non-identity rotation. Okay, so the identity rotation fixes everything. So of course, this condition will be trivially true all the time if you're allowed to include the identity here, but here we're just looking at the non-identity rotations. The other way to write this condition that's equivalent is that you look at the stabilizer in G of S, and you want that to be non-trivial. Remember, this is a subgroup of G, so it always includes at least the 1, and the point is that if it's actually bigger than 1, then this S satisfies this condition here as well, and in that case we call it a pole of this subgroup G. Okay, so let's see why these two are equivalent, and what we'll do is we'll look at this equation essentially here, G dot S equals S. Okay, so firstly we'll do that, and what we can do is we can fix S and think of this as a condition on G. If we fix S, okay, then what are we saying about G? G just stabilizes S, so G is in the stabilizer of S. If instead we kind of fix G and we look at it as a condition on S, what do we have? Okay, so G fixes this S, so S is fixed by this G, so S is in the fixed point set of G. Okay, so of course these two conditions are equivalent here. Okay, let's see how that immediately gives you the fact that A and B are equivalent as well. Okay, so suppose you have some element inside here. Okay, S is inside SG for some non-trivial G. So you're inside here. That means what? That means that this G is inside this stabilizer group, and the G wasn't the identity, so some non-identity element G is inside here, so this stabilizer is not equal to 1. And in the converse direction, suppose you have something that's not 1 inside here, so G is inside here, but it's not 1. Okay, then S is inside that fixed point set. So you have S is inside that fixed point set for that particular G, which is not 1. Okay, so A and B are equivalent, and that gives you a definition of poles. Okay, so I want to move to a fairly general setup where we just still have just G, any subgroup of SO3. And this is a rather interesting proposition here. It says that the G action on S, okay, so certainly G acts on this unit sphere, it restricts to an action on the set X of poles. So we're going to look at all the poles of this group G. Okay, look at the set of all of them, and the point is that the G actually restricts to an action on this set of poles. Okay, so it acts on S, and what we need to show that if you're given a pole, of course, you can let the group act on it, so you rotate that pole, and the point is for it to stay inside that X, you want closure under the group action, so you need G dot S also to be a pole. Okay, so that's the content of this proposition, and let's check why that's true. So it's easiest to do that using condition B. To check that something is a pole, or to say something is a pole, just means that its stabilizer is non-trivial. Okay, so if S is a pole, its stabilizer in G of S is non-trivial. To show that G dot S is a pole, you want to show that the stabilizer of G dot S is non-trivial. Okay, so not 1. But the point is that we know the relationship between the stabilizer of G dot S and the stabilizer in G of S. Okay, this stabilizer is just a conjugate of this stabilizer. G stabilizer in G of S times G inverse. And it's quite easy to see that as once this is not equal to 1, this is also not equal to 1. Okay, they're if and only if. In fact, they have the same number of elements. Okay, there's a bijection between the two where you map an element in here to G, that element, G inverse. Okay, there's the bijection. Okay, so that immediately gives this lovely proposition here. Okay, so if you have any finite subgroup of G of SO3, then you can look at its set of poles, and that set of poles actually is a G set. Okay, so let's go back to our original question. Okay, can you recover a Platonic solid from its rotational symmetry group? And this is only up to duality. And you can more or less do that. And that's the point of what I've set up here. Okay, so let's see how we want to do that. Okay, so I guess if you want to recover the Platonic solid, what do you want to do? You basically want to recover, for example, what are all the vertices? And then how do you join the vertices to get the edges? And then how do you piece the edges together to get the faces? Okay, but it's pretty clear once you've got the vertices, and definitely even more clear once you've got the edges as well. And then with the final piece of information with the faces, you have the Platonic solid. Now, of course, you can't do it completely because you can't distinguish between the faces and the vertices because of duality. Okay, so that's something that we need to keep in mind. Okay, but let's just see how that happens. Okay, so what does the rotational symmetry group tell us about the vertices, the faces, and the edges? Okay, so remember, for each rotation that's in the rotational symmetry group, okay, they come in 3 flavors. Okay, so they either go through the axis of rotation, either goes through a midpoint of a face, midpoint of an edge, or through a vertex. Okay, so of course it has to shoot out the other side as well, so that one may be the same type of thing or might be different. Okay, so in any case, they're the possibilities that you have. And of course, maybe you want to get at all the vertices. Okay, so how do you get something which corresponds to each of those things? Okay, well, of course, if you look at a rotation, for example, which goes through the middle point of this face, you can look at the 2 poles. And those 2 poles will correspond to the top and the bottom face. Okay. If you want to try to get a handle on the vertices, well, you can look at the rotation through that vertex. Okay. And for example, rotation across this diagonal vertex here. Okay. That has 2 poles, and they correspond to the 2 vertices here. And similarly for the edges. Okay. So the poles really give you the set of edges, faces, and vertices. Okay, so that's great. That gets you almost at least something to work with if you want to try to recover the Platonic solid. And then the only question becomes, well, how do you distinguish those sets which, those poles which correspond to faces, those poles which correspond to edges, and those poles which correspond to vertices? How do you divide them up into 3 classes, okay, so that potentially they give you a Platonic solid? And the point is the following, okay, and this is again where we use maximal symmetry of these Platonic solids, okay? So remember, all the faces look the same, okay? So that means that you can send one face to another face, and so the corresponding pole also gets mapped in that way, okay? So in other words, you'll easily see that all the poles corresponding to faces, okay, they form one G-orbit in this G set of poles. All the poles corresponding to edges, they'll form a second G-orbit, and all the poles corresponding to vertices will form a third G-orbit. So now you've broken up this set of poles X, and they correspond to, their points correspond to the edges, the faces, and the vertices, okay, but they're all jumbled up at the moment. And to separate them out into the 3 things, okay, you just have to use G-orbits, okay, and that'll break it up into 3 things. Now, of course, you then have to say, well, which ones are the faces, which ones are the vertices, and which ones are the edges? And of course, it's impossible to actually distinguish between the 3 of them because the faces and the vertices can get swapped around. But actually, if you look carefully, it's quite easy to say which one has to be the edges just by the numerology and the number, and we'll go through that when one thing that I do want to show in another video is how we classify the Platonic solids and the finite subgroups of SO3 at the same time. I hope you enjoyed this adventure in pure mathematics.